Okay, so we are basically, as I was saying previously also, we are talking about astrophysics, right? Physics of astronomical objects and all that. So, what is the central point which separates the study of astrophysics from all the physics studies that we have done previously? And if you will remember carefully, the central point is the importance of gravity. Till now, in classical, electromagnetic, all that, we have stuff, optics, nuclear physics, condensed matter physics. We have talked about mainly electromagnetic interaction, strong interaction, weak interaction and all that. Gravity sometimes it entered the discussion, but never was a scenario where we just talked about the importance of gravity and the various structures possible due to gravity. We didn't talk about it, and this is what we will do in this course, astrophysics. So how do we proceed? Basically, as we know, there are four important forces: strong, weak, electromagnetic and gravity, as you can see over here. Now out of these forces, the strong and weak, they are quite short ranged, right? Whereas electromagnetic and gravity, they are infinite range, very long range. Okay. Now this is very interesting. The entire atomic physics, nuclear physics, particle physics, we can explain from these two structures. Also this one as well, electromagnetic interaction. But now gravity, I am saying that importance of gravity, I want to highlight. Now if I want to highlight the importance of gravity, what do you think? Where will gravity compete with out of these four? Now these are very short interaction. Suppose look into this structure, this hand. Okay. Do you think out of all these forces, which one is responsible for by this, or maybe for the structure of this chalk? Which one is responsible? Electromagnetic in broad sense, right? But again, is it really electromagnetic? How can you get the atoms and nuclei if not for the strong? And even the weak interaction also plays a very important role. Okay, so in fact, if you think carefully, the broad answer is electromagnetic theory, but both strong and weak play important role in the structure of this chalk, or even the structure of my hand and all the stuff. Why my hand is like this and why my hand is not floating in a liquid form. Okay, something like that. But what about gravity? This poor child doesn't even have a place over here. Now, let's try to find a place for this poor child. Now, as you can see, these two forces are very large, infinite range. So, gravity, the competition will be with electromagnetic force, since both are very large range. Now, another very interesting thing is that electromagnetic interaction, it basically depends on the charge. Although it is long range, but only if there is very charge, right, presence of charge, then only it will be coming into play. Even if there are neutral particles, then there will be, if they are very close to each other, neutral particles, then there is sort of polarization and all that stuff. But mainly important thing is if there is charge. Now, let us try to compare these two forces very broadly, which are very infinite range. Okay, this is the first point. So, let us start with a body, mass m, radius r, spherical body, basic case. Now, let n be the total number of particles in the body. I am assuming atoms are there. Very basic assumption. Atomic mass is mp, atomic radius is a0. No issue at all. Now, let's first talk about the electromagnetic interaction. So, we have got a very normal matter where electromagnetic force is important. So, what's the atomic binding energy? Of the order of charge square by dimension, that is q square by a0, atomic radius, and this is the electric charge. Now as I was saying, suppose these atoms are inside this body, these atoms are closely packed, okay, and there are capital N atoms in this V volume. So this is the volume is V, the body's volume is V. So I can write volume of one atom as V by N, and so this is equal to 1 by N, basically number density, something like this, very simple. Now again, this volume of one atom, you can write it in a different form is as 4 by 3 pi A0 cube or roughly A0 cube. Now these two are roughly the same. So from there, if we equate these two, we get this relation, N into A0 cube equal to 1. Now if I put this over here, then more or less I will get this sort of relation. So the atomic binding energy, or where the electromagnetic interaction is important, is of the order of q square into n to the power 1 by 3. Now let's talk about the effect of gravity. Let's try to find the gravitational energy per particle. So as usual, G mm by R. Now this is the total mass m, and this is the small okay, per particle mass m by n. Now I have done the very simple deductions over here. So total mass equal to total mass is total particles into mn. Okay, what's the total volume? Again n into volume of the individual. This is approximate, remember, because there will be some part left. Okay, now from here I am getting this relation between R and capital N. Okay, now if I incorporate this over here, then this is the form that I am getting. Right, now again, similar to this form, I can write N as N by V into V. Okay, from here I am getting the relation between N and capital and small n. Now if I include all these terms over here, then I am getting this relation, epsilon g proportional to gmp square n to the power 2 by 3 into small n to the power 1 by 3. Now look into the structure. What do you see? This is a constant, right? Whereas here, this is a constant. Both have n to the power 1 by 3 dependence, both. But here we have got this term extra, number of particles. And this is what will make this poor child important. Okay? Okay, so we have got this atomic binding energy and the gravitational energy per particle, right? Now, let me talk about the fine structure constant alpha, approximately q square by h cross c. Thank you. So, this is approximately 1 by 137. Okay. Now, let's talk about the gravitational fine structure constant. Remember this fine structure constant, this is importance of electromagnetic interactions, right? There we obtained this result. This structure we encountered during our course of electromagnetic theory. Now similarly, we have got this important another constant, which is gravitational fine structure constant, and it looks like this, G mp square by h cross c. Look into the similarity of the structure. Here we have got q square, here we have got g mp square. That is the strength of the interaction. Charge, strength of electromagnetic interaction, gravitational constant into mass, strength of the gravitational interaction. Okay, now remember these values as well, 1 by 137, 10 to the power minus 38. In a way, if you compare these two structure constants, you can immediately understand how much weak is our poor child compared to this. Okay, but let's see how it goes. So now let us compare. Now we can do two types of comparison. One is subtraction or another is division and comparison. Here division is much better because if we do a subtraction, it will not be effective because these two are varying by a very large amount. Let's do the division sort of stuff. So epsilon A by epsilon G, that is Em by gravity. Em by gravity. Okay. So you see these two expressions I can boil down in this form over here using these structure constants. And again, if I introduce a new constant which is epsilon by epsilon g to the power 3 by 2 known as mg, if I introduce this, then this comparison simply boils down to this result. Now if you estimate it very simple, you will get this is the value. So overall, when will electromagnetic interaction become important? When this is smaller than 10 to the power 54. But the moment n approaches this value, then our poor child will start becoming important. Okay. So now let me show you some important results to appreciate. Okay, so as I was saying previously, we are doing all these studies, we are enjoying our life on earth, right? Okay, and the interesting thing is that here gravity is important, but not only gravity, electromagnetic force is also important. Okay, so here you can see an importance of this. So as I showed you over here, electromagnetic by gravitation, this is of the order of 10 to the power 54 by n. So when n approaches this value, which is basically mg, then gravity starts becoming important. As the simplest scenario where gravity becomes important is a planet. You can check for yourself, right? So here you see, let us try to find the mass of a planet. Just multiply total number into basic atomic mass. It comes out to be 10 to the power 30 grams. Okay. What about the radius of the planet? Ng to the power 1 by 3 into A0, which is of the order of 10 to the power 10 centimeter. Remember, when I am talking about planet, I want to say that here, apart from strong, weak electromagnetic, for the first time now gravity has started becoming important. Okay. So let's try to compare with the case of Earth. What's the mass? 6 into 10 to the power 27 gram. See? Lower. Radius 6 into 10 to the power 8 centimeter. What about Jupiter? Largest planet known, right, in our solar system. Mass around, see the range, 2 into 10 to the power 30 centimeter. Look, so nice. What's the radius? 7 into 10 to the power 9 centimeter. So more or less approaches this limit. So in this planet, we have, if we talk about the astrophysics of planet, we will have to consider not only physics but also chemistry. Why? Because their electromagnetic interaction will also become as important as the gravity. Okay. Now what about stars? See, sun, what's the mass? 2 into 10 to the power 33, more than 30. What's the radius? 7 into 10 to the power 10, more. So this means stars are objects where gravity is now becoming the most dominant force. Okay, and that's what we have done. We will be doing, you can say. So we will be talking about the importance. We will be talking about physics, but this is important. Okay, so you can just compare this for yourself. So in a very basic way, we have tried to understand, or we have tried to find the structure where gravity will start becoming important, and this is the scenario for planets. Next time I will talk about galaxies regarding their structure.